Alright, silly people, here's the situation. We're going to do some proofs involving the traces of matrices. One of them that if we take the trace of two matrices multiplied together, T1, T2, that it's equivalent to taking the trace of the same two matrices multiplied in the opposite order, right? Um, so to do this, we have the definition of a trace, right? So we can write that the trace of two matrices multiplied together like this will just be sum over I uh, to m, and it's going to be the indexed version of the two multiplied matrices together, indexed I. Now we know how matrix multiplication works. I think the way that Griffiths defined it, he says that UIK equals sum over j to n, actually. It's TIJSJK, where the multiplied matrices are TS, right? So here we have a sum over j now to the n, right? But we have T1, which I'm going to put the indexes up top, actually. It's going to be IJ, but then T2 will be indexed JI instead of JK because it's indexed II, right? So it's that. Uh, so we have a sum over I to M and a sum over J to N, but M is actually equal to N because both of these numbers just represent like the size of the matrix, how many rows it has, how many columns it has. So therefore we can replace the indices freely. So this is equivalent to saying that it's equal to I to the 1 m, sum over j equals 1 to the n, tji 1, t2 ij. And if you rearrange that to look more like the original matrix multiplication formula, it looks like T2ij, T1ij. No, T1ji is what I meant. T1ji, which is actually just the sum over I to the m of T2, T1, II, which is actually just the trace of T2, T1. So this is up here a true fact, true identity that we've just proved. So Griffith says it follows that the trace of three matrices multiplied together, T1, T2, T3, is the same if you reorder it as trace T2, T3, T1, just because two matrices multiplied together can make a new matrix, S, and then you just flip the order of S and you get T2, 3, and T1. So that's true, it does follow immediately from that. But does it equal to the trace of the matrices in this order? T2, T1, T3. And Griffith suggests that we supply a counterexample to disprove that you end up getting this same sort of thing. Counterexample that I found worked was if we set T1 to be this two-dimensional matrix 0, 0, 1, 0. This T2, we set it to 0, 1, 0, 0, and we take T3 to be 1, 0, 0, 0, and then we just calculate both sides of this supposed inequality. So first, we'll calculate the trace of T1, T2, T3, and you get that it's the trace of put it in square brackets here. 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0. So you can do a little bit of matrix multiplication at this point. And then you can be like, this is bam, bam, this is 0, bam, 1, 0, and then 0. That's what that matrix looks like. And then multiply those two matrices that are left, and you get 1 here, and then 0, and then 0, and then 0. Yeah. So the trace of that is obviously 1, because you just add up that one diagonal element, you get 1. Compare this to the other trace that we wanted to do, the trace of T2, T1, T3. And we get that that's equal to the trace of, in square brackets, 0, 1, 0, 0 times 0, 1, 0, 0 times 1, 0, 0, 0. So we take the trace of this matrix multiplied by the product of those two matrices, which is actually 0 here, 0 here, 0 here, and 0 here. So we get that it's the trace of the matrix 0, 0, 0, 0, which is obviously 0. So no, they're not equivalent. Fancy that.